Hello viewers. Today I'm going to introduce you the Schottky diode. This video consists of introduction, diode configuration, basic operation of the diode, characteristics of the diode, future trends in device development and applications, and lastly conclusion. Let me start by introducing myself. I'm Movinesh Devar, a year 1 university student, and in this video I'm going to provide a detailed elaboration of Schottky diode. So moving on to the topic, a Schottky diode is known as hot carrier diode because electrons present in the N side get sufficient energy to cross the junction barrier and enters the metal during forward bias. The electrons entering the metal and with tremendous energy are known as hot carriers. Thus, the diode is called a hot carrier diode. They are also known as low voltage diode as they have the lowest forward voltage drop for a given current. The Schottky barrier, named after Walter H. Schottky, is referring to a potential energy barrier for the electrons formed at the diode. As we look into the diode configurations, based on the diagram on the right, we know N-type silicon semiconductor is joined with a metal electrode to produce metal semiconductor junction. Unlike the PN junction diode, the Schottky uses metals like gold, tungsten, platinum, or aluminum instead of the P-type semiconductors. The width of this metal semiconductor junction varies based on the type of metal compound and semiconductor materials used in its construction. During forward bias, the depletion region is reduced, causing electrons move from the N-type material to the metal electrode, allowing current to flow. Thus, current through the Schottky diode is the result of the drift of majority carriers. And during reverse bias, since there is no P-type semiconductor material, therefore no minority carriers, so the depletion region increases and the diode's conduction stops very quickly and changes to blocking current flow. Next is the basic operation of the diode. In a Schottky diode, there is a Schottky barrier, which is a depletion layer formed at the junction of the metal and N-type semiconductor. The electrons have to overcome the potential energy of this Schottky barrier in order to flow across the diode. In case of Schottky diodes, N-type semiconductors have higher potential energy than electrons of metals. Therefore, when the two are brought into contact with each other, there is a flow of electrons in both directions across the metal semiconductor interface. The voltage is applied to the diode so that the metal is positive when compared to the semiconductor. The voltage opposes the built-in electric potential and makes the current flow easy. Following on to the characteristics of the diode, based on the graph above, we can understand that the Schottky diode, which is on the left, has a lower forward voltage compared to PN junction diode, which is on the right, with a difference of 0.3 volt. Lower turn-on voltage causes faster switching time. This means that a smaller forward voltage drop at a given current will result in less power dissipation than the PN junction diode. In plain English, the Schottky diode doesn't get as hot as a regular diode. These diodes also have a lower recovery time because Schottky diodes are a unipolar device, thus causes short reverse recovery time. The only disadvantage of Schottky diode is high reverse leakage current. Due to its unique metal semiconductor junction design, which creates a lower barrier for current flow in reverse bias, resulting in higher leakage current when a reverse voltage is applied. The future trends in device developments involving Schottky diodes are automotive electronics that requires high efficiency and low power losses. In the automotive industry, this translates to longer battery life, faster charging times, and improved energy efficiency for electric vehicles. Telecommunications are one of the future trend too, as Schottky diodes can be nanostructured to improve their dielectric constant, which could lead to faster communication. Schottky diodes are the best semiconductor devices to use in power rectifier applications because these devices have both a high current density and low forward voltage drop, causing lower heat levels and an overall increased efficiency of the electronic system. Schottky diodes have high switching speeds and high frequency capabilities, making it well equipped for radio frequency applications. Schottky diodes can be used in power OR circuit applications where current is generated by two parallel power supplies because of their low forward voltage drop, preventing reverse current flow from one supply entering the other. Schottky diodes can be used in solar cells to prevent the batteries from discharging through the solar cells at night. Last but not the least, it is concluded that the Schottky diode are used in many applications because of their low turn-on voltage, fast recovery time, and low loss energy at higher frequencies, mostly in digital circuits. They work on the principle that the electrons in different materials possess different potential energy. It has a low forward voltage drop, almost equal from 0.15 to 0.45 volt. Therefore, it's been widely used in the industrial field. Thank you for watching.